So bean packing uh, problem which can be solved by approximation algorithm. So today we are going to discuss this one. So what happens in bean packing is that given n items with sizes s1, s2 up to sn, such that si is within the range of 0 to 1 for I is within the range of n to 1. Pack them in minimum number of unit capacity bin. That is a bin packing algorithm. So this problem is an NP complete problem. It has no solution in polynomial time, but as the number of items are less here, before that let us see this. What is the size of the bin? This is a 1 unit bin size, and let's say that we have 9 items here, and each items are zero point 0.5. The size is 0 0.5, 0 0.7, 0 0.5, 0 0.2, 0 0.4, 0 0.2, 0 0.5, 0 0.1 and 0 0.6. This is in random orders. So we have to fill this bin with these items so that we have minimum number of bins and maximal element we can actually push inside the bins. That is the bin packing. You have to pack them. Uh, so as I mentioned, it has no polynomial solution, but what could be the optimal solution seeing this 9 items? The optimal solutions could be this, because here optimal solution visually we can see, and we can actually get the results optimally because number of items are less. Okay, but let's see what could be the optimal solution. However, there is no solution in polynomial time for bean packing algorithm. That means optimally there is no solution available. So it's a NP complete problem. In fact, it is NP hard problem. So no one is able to solve this, but we can definitely approximate it. But let's say the number of items here are 9, so we can check visually how it can be the optimal solution could have been. But when the number of items will be large enough, then these problems will go beyond our reach. Nobody can solve it in polynomial time. But let's see optimally if we would have done it. So what will be the solution? So here you can see that first item, I mean the zero point 0.5 and 0.5 can be pushed here in the bin 1, and 0.7, 0.7 and 0.2 can be pushed here. So 0.9 will be contributing to 0.9 total, and then here in the third bin 0.5, 0.4 and 0.1, which is totally 1 unit will be consumed. Each bin size maximum is 1 unit, so more than 1 unit is not possible to push inside the bin. And the fourth bin can have 0.2 and 0.6. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Total 9 items can be accommodated here. So optimal bin size, optimal number of bins that are required is 4. However, as I mentioned, this problem is unsolvable. Nobody can find optimal solution. So this solution is not possible in polynomial time, as it is NP hard and NP complete problem. So we have to approximate it. There is no other choice. Why we are able to do it here? Because number of items are less. So visually seeing, we can do a small solution, so it is very trivial by nature. Now let's see how we can do it. Approximation algorithm, it has 3 types. One is the next fit algorithm. So in next fit algorithm, what happens? This algorithm checks if the current item fits in the current bin. If so, then place it there. Otherwise, start a new bin. Very simple algorithm. Okay. So first, whichever item comes, you just keep pushing, and then if the bin has the remaining size so that it can accommodate the next item, so you just do it. So let's say first item is 0.5, we are pushing it in bin 1. Second item is 0.7, so we cannot push it to bin 1. We have to create a new bin. We have to build a new bin where we are pushing 0.7. Now now again we are encountering with 0.5, so 0.5 cannot be pushed in bin 2 because already 0.7 has been occupied here in bin 2. We cannot go back to bin 1 in case of next fit algorithm, because in this case it is always next like that will go. So then we have 0.5 third bin. 0.5 is accommodated in third bin, and next 0.2 we can accommodate in bin 3 itself, so total it will be 0.7, so it is okay. Next 0.4, but 0.4 you cannot keep in bin 3 because again it will be more than 1 unit, so we have to create a new bin where you can keep 0.4. After 0.4 again 0.2, so 0.2 you can keep it here, no issue. Then 0.5 we cannot keep it here, so we have to create a new bin for it, as it is a next fit algorithm. So point 5 is here, and then point 1 you can keep it in bin 5, and then finally point 6 you can keep in the bin 6. So this is how we can accommodate all items in the bins. However, it is not that good algorithm because it's an approximation algorithm which will always be lagging from the optimal solutions. So number of bins are 6 here. So if m be the optimal number of bins required to pack a list of I items, next fit will be almost twice m bins. So it will not be more than twice m. So optimally in the last slide we saw that it was 4 bins. So here it is 6 bins. So 4 into 2 is 8. So 6 is however less than 8. So it's okay. It will be less than or equal to twice m bin. So this is persisting, right? These exist sequence such that the next fit uses 2m minus 1 bin. So this is where our next fit algorithm. Next, go to the next algorithm. First fit algorithm. This is a second algorithm, right? So this algorithm, what it says, the next this technique checks the bin in order and place the new item in the first bin that is large enough to hold it. A new bin is created only when an item does not fit in the previous bin. So in the next fit algorithm, we are just checking the current bin. If the current bin is not able to accommodate the items, then you are creating a new bin. Here it is not like that. Here you can go to the previous bin and you can check whether the place is available, or the space is available or not. You can go to the earlier bins also. So here you so so point 0.5 here, point 0.5 first bin, in the first bin, point 0.7 second bin, point 0.5 again accommodate to the first bin, then point 0.2 accommodate in the second bin, then point 4 in the third bin you have to accommodate because bin 1 and bin 2 already exhausted. Then point 0.2 you can keep in the third bin again because it has the space. Then again point 5 cannot be accommodated neither in bin 3 nor in bin 2 nor in bin 1. So we have to create a new bin which is, and then finally point 1 you can accommodate in bin 2 because bin 2 is zero point 0.9. So total size is maximum 1 unit. So it is 0.9 is okay, fine. 0.9 plus 1 unit. So totally it can accommodate. So bin 2, I mean in bin 2 0.1 can be accommodated, and finally you have 0.6 which we need a new bin because neither you can accommodate in bin 4, bin 3, bin 2 already exhausted, and bin 1 is not possible because already it has 1 unit. So you have to have this bin 5. This is called first fit algorithm. So first fit algorithm, let m be the optimal number of bins required to pack a list of I items. First fit will never use more than 1.7 bins, 7m bins. There exists a sequence such that first fit uses 1.67m. Okay, so this is what first fit algorithm does. It cannot go more than 1.7m. So this is how it is. Okay, m is the optimal bin that we calculate in the first case. Now finally go to the, so next is best fit algorithm. So best fit algorithm, in this algorithm what happens, new item is placed in a bin where it fits the tightest. If it does not fit in any bin, then start a new bin. That is the algorithm says. A new item is placed in a bin where it fits the tightest. If it does not fit in any bin, then start a new bin. It can be implemented in O n log n time. Let us see how this algorithm works. So these are the items mentioned. So let's say, so it says that item is placed in a bin where it fits the tightest. So first point 2 will be trying in bin 1, and then point 5. Now bin 1 already has 0.8 space, so it will be placed, 0.5 will be placed here. Tightest fits you have to find. Okay, so 0.5 also can be accommodated in bin 1. Then point 4 cannot be accommodated in bin 1, so we have to create a new bin which is bin 2 where point 4 is there. Point 4 is pushed. Then point 7 cannot be accommodated neither in bin 1 nor in bin 2, so new bin created where we have pushed point 7. Then point 1 we can see that bin 1, which is, every bin has 1 unit of total space, out of that point 7 has been used, so point 3 is still there in bin 1, so point 1 can be accommodated in bin 1. Okay, so again let us start. So this best fit algorithm says that new item is placed in a bin where it fits the tightest. If it does not fit any bin, then start a new bin. So tightest fit you have to look at. So first point 2 in bin 1, then point 5, then point 4 cannot be accommodated in bin 1, so we can create a new bin which is bin 2. Then you have point 7. Point 7 also cannot be accommodated in bin 1, neither it can be go to bin 2. So new bin is created. Now point 1 we can have here in bin 1, because if it is the case, then bin 1 will be like somewhat it going towards tightest fit. Then point 3 we can keep in in bin 2 also, because bin 2 has already point 6 available space, but we will keep it in bin 3, because then only it will be tightest, then will be full bin will be occupied. Then point 8 again you can push it in bin 4, which is a new bin. This is how the best fit algorithm works, and this is the optimal fit that you already have shown earlier. Okay, so here tightest fit you are looking for. So point 2 goes to bin 1, point 5 also goes to bin 1, point 4 cannot be accommodated in bin 1, so we create a new bin point 4, which is bin 2. Point 7 neither can be placed in bin 1 nor it can be placed in bin 2, so new bin created here. Once point 1 came, we can keep point 1 in bin 2, bin B2 and bin B3, but we won't do it. We will keep it in bin 1, because then only it will be tightest utilization of the bin. And then when points 3 come, we will not keep it in bin 2, we will keep it in bin 3. Then only full occupation will happen in bin 3. And then finally bin 8, which cannot be placed in neither bin 1 nor bin 2 nor bin 3, so new bin will be created. This is best fit algorithm. Okay, and it takes O n log n time by using a balanced binary tree sorting bins order by remaining capacity. Thank you very much.